So how does the Wronskian work? How does the Wronskian prove that certain things are linearly dependent? So how does Wronskian work? Okay, so here's our goal. I want to say C1 f of x, C2 g of x plus C3 h of x equal to 0 implies that C1, C2, C3 is equal to 0. And I want to prove that if the Wronskian of FGH is non-zero, then this is implied. This automatically works, and therefore it's independent. So let's see how that works. Okay? So claim if the Wronskian of FGH is not equal to 0, then above is true. Okay. In other words, FGH are linearly what? Dependent or independent? Independent. I mean, if 0, 0, 0 is the only way you can satisfy this, that means there is no linear relationship among the functions, and they're totally independent from one another. Okay? That's what this is saying. Okay? All right. Okay, proof. We start from C1. C2 and C3 like this. This is our given, and we want to show that C1, C2, C3 are all equal to 0. Okay, because C1, C2, C3 are constants, I can differentiate both sides. I can differentiate. And what's the derivative of the left side? C1 f prime of x, C2 g prime of x, C3 h prime of x equal to 0, right? And I can differentiate one more time. And I get C1 f double prime of x, C2 g double prime of x, plus C3 h double prime of x. Now, I can take all of these and write it in terms of a matrix equation. Okay, so look at this. If I choose fx, gx, hx, and then f prime of x, g prime of x, h prime of x, f double prime of x, g double prime of x, h double prime of x, a, b, not a, b, c, sorry, c1, c2, c3. Equal to 0, 0, 0. This matrix equation encodes exactly these three equations you have above. Okay? Now, in case if you forgot how to multiply matrices, let me remind you again. You multiply matrices by doing across and down, right? So you do across, down, and when I choose one row and one column to do across down, I mean I'm doing the dot product between the two vectors. So here's a row vector, here's a column vector, and you have to do dot product. What's a dot product? You do component-wise multiplication and then you add the result, right? So look at what you have. Fx times C1, Gx times C2, Hx times C3, and you add them up. What do you get if you do that? You get the very first one, right? Yeah. Equal to the first element, which is 0. And you get the same thing. Across down, f prime of x times C1, g prime of x times C2, h prime of x times C3. That's what you get, and that's equal to 0. So this thing here encodes exactly what we have above. Okay? Now, then, doesn't this look awfully similar to what we were trying to use? What is this like?
Wronskian.
It's like the Wronskian. What's the difference? This is a matrix, but the Wronskian is the determinant. What does determinant has anything to do with the matrix?
Inverse.
If it's non-zero, we know that it has an inverse function. So if I call this A, then the Wronskian of f, g, h is really the determinant of A. And if this is not equal to 0, if this is not equal to 0, that means determinant is not equal to 0. That means the inverse of this function exists, right? So here's how the above looks like. You can rewrite this as A times C1, C2, C3 equal to 0, 0, 0. And then, since determinant is not equal to 0, the inverse function does exist. And if it does exist, I can multiply A inverse both sides. So I have A inverse times A times C1, C2, C3 equal to A inverse times 0, 0, 0. What's A inverse times A? They cancel. It's identity matrix, but they cancel. What's any matrix times 0, 0, 0? 0, 0, 0. So what did we just prove? We proved that C1 is 0, C2 is 0, C3 is 0. So that's how the Wronskian works. Okay. Yeah. Since we have 5 more minutes, let me show you another example to elaborate the power of Wronskians. Okay. So example. Suppose we found 2 solutions to y double prime equals to 4y as e to the 2x and e to the 2x plus 1. Question. Can these form the general solution? What do you think? What's your hunch? Can we use these 2 solutions? I mean, you can actually show that they are individually solutions. If you differentiate this twice, every time you differentiate, 2 comes in front, right? So if you differentiate twice, you get 4, which is exactly this right side. Okay? So you can check that this is a solution. You can also check that this is a solution, so we have 2 solutions. Question is, can we use them to form the general solution? In other words, can we just say y equals to c1 e to the 2x, c2 e to the 2x plus 1? We have 2, now we're done. Okay. Can we say that? Are we happy with this solution? Yes or no? We can't say yes or no unless we check for what? Linear independence. If they are dependent, then it's no good. We have to find something else. Okay? If they are independent, then we're happy. We can say this is the solution. Okay? So how can we see that these are linearly dependent or not dependent? independent. Wronskian, right? So let's take the Wronskian. The Wronskian in this case is either 2x plus 1. What goes here?
2 e to 2x.
2 e to the 2x, thank you. And how about here?
2 e to 2x plus 1.
2 e to the 2x plus 1. Okay, now we do this, which is e to the 2x times 2 times e to the 2x plus 1 minus e to the 2x plus 1 times 2 times e to the 2x. And the result is
0.
0. That means
Dependent.
they're dependent, so no, this is bad, okay? They're dependent. It's no good.